Hi everyone and welcome to this virtual talk. Today I'm going to tell you a bit about this concept of palette sparsification for graph coloring problems beyond Delta+1 coloring. And this is joined forth with Nogala. So quick reminder on graph coloring. A C coloring of a graph is simply an assignment of colors 1, 2, or up to C to the vertices of the graph so that no edge has the same color on both its endpoints. So for instance, this is a 5 coloring of this graph. And as a notation through this talk, I'm going to use n to denote the number of vertices, and delta is going to be the maximum degree for me. Now, one of the very first things one learns about graph coloring is that every graph can be colored with Delta+1 colors. The reason is simply that we can greedily color the vertices. For instance, whenever we reach a vertex, even if we have used a different color on all of its neighbors, still there will be a color that we can assign to this vertex and color the entire graph. So now let me ask you a question about Delta+1 coloring. Remember that in this problem, we have started with the same palette of Delta+1 colors for all the vertices, and every vertex could have chosen its color from this palette. Now I'm asking, is there a way that we take these palettes and shrink them separately and perhaps differently across the vertices so that we are still able to color the graph? Which means that we can, every vertex still can choose a color from its own palette, and the final coloring is a valid coloring of the graph. And to make sure, I'm not asking for you to color the graph greedily. Any way of coloring the graph is okay with me as long as there is a way to color the graph. Good. Now, for instance, if we started with this example, we want to shrink them perhaps to something like this, and then choose the color of every vertex from its own palette to color the graph. Good. Now, if you think about it a bit, this question is not really that interesting question. The reason is simply because it has a very trivial answer. Yes, of course, we can shrink the size of every palette to just one by first finding a Delta+1 coloring of the graph and then assigning that color for each vertex to its palette. And then definitely we can color the graph using the palettes. So in fact, the question that I'm really interested in is something slightly different, and it's the following. Is there a way that we can shrink the size of this palette without even looking at the graph first and still color the graph? And for us to be able to have any chance of getting a positive result here, we should allow for randomization. So you pick the color of the vertices, the new palettes of the vertices randomly without looking at the graph. And we want to be able to pick a small number of colors per vertex so that the graph is still colorable with high probability. But this palette sparsification question was first asked in a joint work of myself with Yu Chen and Sanjeev Khanna back in 2019, and I'll get to the motivation of this question in a second. But there we proved the following theorem. If for every vertex, we sample order log n colors independently and uniformly at random from 1 to 2 to Delta+1, still we are able to, with high probability, color the graph using these much smaller palettes. We started with Delta+1 and shrink them down to log n randomly. And we proved that we are still able to color the graph with high probability. Good. And now the question of why we ask this question. Well, on the surface first, this is, I think, a very nice combinatorial question on its own that's worth studying. But the reason we ended up with this question was, in fact, as a way of trying to design a different type of algorithm, or perhaps even more efficient algorithm for the Delta+1 coloring problem. So let me tell you a bit about that aspect first. The interesting thing about this palette sparsification is that not only it reduces the number of colors per each vertex, in fact, it also dramatically reduces the number of important or relevant edges in the graph. So let's say this is my graph again, and then we sample these colors randomly. And the important observation is that most of the edges of the graph are not important for us anymore. In fact, we only care about an edge if the palette of this edge, the palettes of the vertices on both sides of this edge are intersecting with each other. Otherwise, that edge is not going to affect the final coloring of the graph. Okay. And so we can remove a bunch of edges from this graph. And it's a very easy calculation to see that because we are picking two random sets of size log n from a universe of size delta, the probability that they intersect is roughly log square n over delta. And so each edge is going to remain in this graph with a very low probability. And when you multiply this with the total number of edges, which is at most n delta, we got that the total number of edges in this graph after doing this palette sparsification with high probability is just roughly n, basically n times log square of n. So why is this useful? So now you see that this gives us a way of getting a graph with potentially n delta edges and reduce its edges to only O tilde of n edges. Okay, so we reduce the dense graph into a relatively sparse graph. Okay, and if we can color this graph, we still obtain a delta+1 coloring of the original graph. This is useful in many different settings. Let me just mention two of them. In this ACK paper, we had a bunch of other applications as well. But two main applications are the following. First, it gives us a streaming algorithm. The setting that edges of the graph are arriving one by one on the fly, and we have to process them without storing the edges. This gives us an algorithm that uses only O tilde n space, and we can find the delta+1 coloring of the graph this way. Another way, perhaps, is that we can, in fact, color the graph without even looking at the entire input. Okay, remember that there is a greedy linear time algorithm that solves this problem. However, now using this technique, we can get an algorithm with runtime, which is roughly n root n. Okay. It's a randomized algorithm, but it's quite surprising because now we can solve the delta+1 coloring for sufficiently dense graph even faster than the standard linear time greedy algorithm. In fact, even without looking at the entire input. These were two of the applications of this palette sparsification, and I should mention that these are not only just some numbers that came out of this, both of these results are also optimal algorithms. And prior to this, there were no result known for either of these problems, non-trivial result known for either of these problems. Okay. Good. So now where we are. So I told you about this palette sparsification in question. Hope you agree that it's a mathematically interesting question and it has tons of application. That's basically what else do you need from a problem. So in this work, we are going to study palette sparsification in context of other graph coloring problems and see what other problems admit such theorems. So now with that in mind, let me tell you about our result. We're going to consider coloring problems when we have a number of colors is even more than delta+1 colors, let's say order delta coloring. We're going to consider cases of graph coloring for a special family of graphs that admit coloring with much less than delta+1 colors. And also we are going to look at the low-call version of graph coloring problems, which I'm going to define shortly. So the first result is about graph coloring with more than delta+1 colors. Here we show that in fact for any constant epsilon, we can sample roughly a square root log n colors per each vertex and get a 1 plus epsilon delta coloring of the graph. So if you allow me to use more than delta+1 color, this shows that we can color the graph with roughly square root log n colors as opposed to the omega log n colors that are necessary for delta+1 coloring. And it shows a separation between these two problems in the context of palette sparsification. Second result concerns a setting when we are going to use less than delta+1 colors. And in fact, many graph families of interest do not require delta+1 colors. It can be colored with much, much fewer colors. And a canonical example is triangle-free graphs that they can be colored with roughly delta divided by log delta colors. And here we can prove that for any parameter gamma, not necessarily a constant, if we sample delta to the gamma plus a square root log n colors per each vertex, then we can color the graph with roughly delta over log n delta colors, but there is this parameter gamma that appears here. So to interpret this, if we take gamma to be a very large constant, very small constant, okay, we are going to still get an asymptotically optimal number of colors for triangle-free graphs. But now we are going to sample the number of colors which have some small polynomial dependence on delta. Remember that this is a new term. The previous palette sparsifications I talked about, neither of them have such a term. But in fact, we can show also, and we prove in this paper, that such a dependence on gamma is necessary. So for triangle-free graphs, there's no way to get around this. And then finally, we look at this problem that suppose every vertex want to choose at the very beginning, choose its own color, not from 1 to delta plus 1, but just from 1 to degree of that vertex plus 1. So if a vertex has degree 2, it only has 3 available colors, colors 1, 2, 3. But if its degree is much larger, it's going to have a larger number of colors. And it's very easy to see that if you have so many colors per each vertex, still a graph is colorable without this context of, without this notion of palette sparsification, again, by the greedy algorithm. And now we are able to show that if we sample log n colors per each vertex, this from such list, this graph is still colorable with high probability. This can be seen as a generalization of this delta plus 1 coloring result of ACK. The important thing is that no number of available colors to each vertex is local to that vertex, as opposed to be some global parameter of the graph. And this is this so-called degree plus 1 coloring problem that was introduced by Chang, Li, and Petit in context of some distributed graph coloring problem. And let me mention that the techniques behind this result, even a much simpler version of them, also gives us a palette sparsification for coloring with roughly kappa number of colors, 1 plus epsilon kappa colors, when kappa is the degeneracy of the graph. And this matches, it's roughly matches a lower bound by Bera, Chakrabarty, and Ghosh. So this is the set of our result. We get a square root log n coloring for, let's say, order delta coloring. We get delta to the gamma plus a square root log n samples for asymptotically optimal coloring of triangle-free graphs. And we got that an extension of delta plus 1 coloring to degree plus 1 coloring palette sparsification result. And as a corollary of this result and using this application to sublinear algorithms, we get a lot of new sublinear algorithms. In particular for triangle-free graphs, now we get a streaming algorithm that uses this space of n times delta to the gamma, or its runtime is n to the 3½ plus gamma here. Okay, and you see that the delta to the gamma term that appeared in palette sparsification now also translate into a space and runtime of this algorithm. And in addition to these sublinear algorithms, our result also can be extended to lots of other locally sparse graphs, such as KR-free graphs or graphs with bounded number, or graphs with a sparse neighborhood, etc., using similar but not exactly the same type of techniques. And I'm not going to talk about these parts here. Okay, so I told you about our result. Let me briefly tell you about our techniques also. For the first two results, we are going to use a new connection to this classical result on list coloring. I'm going to define them shortly and talk about them more throughout the talk. And so this is basically a new connection. This is a very different type of proof than what was used in this ACK paper. For the lower bound of the number of colors needed for triangle-free graphs, this is a very nice argument and simple argument based on random graph theory, but it's not a trivial lower bound, like, for instance, that omega square root log n's are needed for ordered delta coloring. And finally, for the final degree plus 1 coloring problem, you notice that this is basically a generalization of delta plus 1 coloring, and we are going to use a very similar approach as the ACK paper. The main difference is this type of graph decomposition that used in this proof. In ACK, we use the decomposition, roughly a sparse dense decomposition, which is based on some very classical result in graph theory. And but those results are really tailored to delta plus 1 coloring. And in this work, we extend them to this degree plus 1 coloring. And maybe this decomposition can be useful elsewhere as well. So for the rest of the talk, let me tell you briefly about how this square root log n sample coloring works for ordered delta coloring. And then I'll talk a bit also about its extension to triangle-free graphs. And I'm going to skip the other parts. Okay, so this is the formal statement of our result. We are saying that for any constant epsilon, if we sample roughly a square root log n for each vertex independent and uniformly at random from 1 plus epsilon delta colors, then G is going to be colorable, okay, with high probability. And every vertex now can choose its color from its sampled list. The proof, as I told you, is based on a connection to list coloring problems. So let me tell you what is list coloring. Remember that in the original coloring problem, every vertex started with the same palettes of colors, and we had to use one color from the palette of each vertex to color the graph. List coloring is the same concept with the differences, but the difference is that now each vertex has its own unique palette, okay? And the palette sizes might be different. The total number of colors used across the palettes can be very different. There's no reason that the palettes are exactly the same. The rest is exactly as before. Now, it's easy to see that palette sparsification is basically a list coloring problem on arbitrary graphs or maybe on triangle-free graphs when we choose the colors when we choose this list randomly from some appropriately sized universe. So it makes sense to look at them from the point of view of list coloring. And the most basic question is that what type of properties we need from lists of a graph so that they are colorable. And the most straightforward property that one can say is that whenever we have lists on the vertices of the graph and size of each list is larger than the maximum degree, we can definitely use those lists to color the graph. Okay? So the first question is that does palette sparsification list satisfy such a property? The answer, and the reason we can do this is just by greedy coloring. And the answer is that no. The reason is that when we are sampling a square root log n colors per each vertex, and even it doesn't matter whatever number we use, the maximum degree of the graph is going to be quadratically larger than the number of size of each list. Okay? So it's not like that the palette sparsification satisfies this guarantee. So we cannot just apply a result like that. Good. So now let's look at what some other stronger properties one can say. And this brings us to this very nice work on the list coloring constants. Basically, let's define the color degree of a vertex color pair to be the number of neighbors of a vertex that contain this color C. So instead of working with the actual number of neighbors, let's just focus on the particular neighbors of V that contain this color C. And there's this nice result by Reed and Sodokov that prove that if size of each list is only 1 plus epsilon times larger than max color degree, as opposed to the maximum degree, then the graph is colorable from the list. Okay? So this is a much, let's say this is a much stronger result than this straightforward coloring property above. And now the question is that does palette sparsification satisfy such a guarantee? At first, the situation is much better. The reason is that now size of each list is a square root log n, and the color degree is also roughly around a square root log n. So that's good. The catch is that these bonds are only true in expectation, and they do not hold with high probability simply because the number of colors we are sampling are not large enough. So still the lists do not satisfy this property, but we are in much better situation. Now let me show you how we can use this to prove the result. Let L of V be the sample list of each vertex V, and notice that for any color in this list, after we do the sampling, the expected color degree of a vertex is going to be the number of lists divided by the size of the list divided by 1 plus epsilon. And the reason is that each vertex has delta neighbors, what chooses its colors from a list of 1 plus epsilon delta. Now, so we bound the expectation, and the neighbors of V are choosing their colors independently. So we can just apply a very simple Chernoff bond to say that the probability that the color degree is going to deviate a lot from the expectation is not large. In fact, the probability that we deviate by more than 1 minus epsilon factor is roughly 2 to the minus a square root log n. Good. This is just Chernoff. Now, that numbers are not good enough to do a union bond over n vertices and also colors, but it means something. It means that if I look at any vertex, not too many colors can deviate from their expectation. In other words, only epsilon a square root log n vertices can have perhaps have a much higher color degree, but the rest are going to be small. And the reason is simply because for more than a square root log n vertices to deviate, each of them with such a small probability, the entire probability is going to become polynomially small, and we can do union bound over all vertices. Now, when we do this thing, we are basically done, because it means that I can remove a small fraction of colors inside the list of each vertex to guarantee that the remaining vertices are going to have a small color degree. And by doing this thing, I did not reduce size of each list too much, and all the numbers will work out, and then we can apply this result of Reed and Sodokov to get the result for palette sparsification as well. And this is basically the proof of the result for order delta, or 1 plus epsilon delta color. Now let's quickly talk about some other improvements. First, omega square root log n colors are also necessary for this, and you can just prove this in by looking at the collection of disjoint clicks. Another nice question is that, can we use this type of result to also prove the delta+1 coloring result of ACK? And it seems that the answer is no here. One reason is in delta+1 coloring, the expected color degrees are basically equal to the size of the list, perhaps maybe just one smaller. This means that even in expectation, even if we didn't have any deviation, this is not enough to apply the Reed-Sodokov result, okay? And in fact, this is something strongly known about these list coloring problems. The condition that size of each list is equal to the max color degree plus 1 is not enough for list coloring. Okay? This is definitely enough when I change this thing with max degree, but this is not enough for max color degree. And so this route does not seem to work for proving the delta+1 coloring this way. Now, finally, let me tell you a bit about the triangle-free graph also. Again, what we want to prove is that if we sample delta to the gamma plus a square root n colors for each vertex from a list which is this time much smaller, this is delta over log n delta, as opposed to be, roughly delta. And if our graph is triangle-free, then we can color the graph with high probability. And this is, again, based on a list coloring result. And something new that we prove in this paper, we prove an extension of the Reed-Sodokov result for triangle-free graphs. Okay? Here, if size of each list is larger than roughly max color degree divided by log of max color degree, we prove that we can still color the graph. Okay? So you see here, for triangle-free graphs, we can actually afford to work with much smaller lists compared to the color degree and still color the graph. And then it's an easy calculation to see that the list of palette sparsification exactly satisfy these guarantees, okay? And we can apply the result. So here the main thing is to prove this new result for triangle-free graphs. And this is basically can be seen as extending the classical result on coloring of triangle-free graphs from max degree to color degrees. This is similar the same way that Reed-Sodokov prove 1 plus epsilon delta coloring. And in fact, the proof of this is also a probabilistic argument and follows closely a distributed algorithm of Petit and Su for triangle-free graphs. So now let me conclude. In this paper, we prove a bunch of new palette sparsification results for coloring with more than delta colors, for coloring triangle-free graphs, and also for degree plus 1 coloring. Now, and they employed a bunch of new sublinear algorithms as well. There are some nice, interesting open questions left here. One is that, can we use these techniques of list coloring perhaps in a different way and get a simpler proof for delta+1 coloring? The other one is that we prove that in context of palette sparsification, this delta to the gamma term is necessary, and it translated into our sublinear algorithms, but we don't know in case of sublinear algorithm whether these type of terms are necessary, or there is a better way, perhaps using entirely different techniques to get those results without such dependence. And then finally, for degree plus 1 coloring, we proved it when each list has to be exactly 1 up to degree plus 1. It's a very nice question to prove it for arbitrary lists of size degree plus 1. And then the final question is that palette sparsification seems to be a nice concept on its own, So can we prove some other palette sparsification or find some new applications? And that's all I wanted to say. Thank you.